Welcome to Agentic AI World, your daily interview prep for AI and software engineering roles. I'm your host, and today is episode 19. Today's topic, AI cost optimization, how to build affordable production AI systems. If you're in an AI interview and they ask, how would you reduce LLM costs in production? This episode is your cheat sheet. Let's start with the core problem. LLMs are expensive. GPT-4 can cost $10 to $30 per million tokens. When you have thousands of users hitting your system daily, those costs compound fast. Companies have blown through hundreds of thousands of dollars on LLM bills without a solid cost strategy. So how do interviewers test this? They ask things like, walk me through how you design a cost-efficient RAG pipeline. How would you reduce OpenAI API costs for a high-traffic chatbot? What's your approach to model selection in production? Let's break down the strategies you need to know. Strategy 1. Right-sizing your model selection. Not every task needs GPT-4. This sounds obvious, but most engineers default to the most powerful model out of habit. Here's the mental model. Classify your tasks by complexity. Simple tasks, classification, intent detection, simple Q&A. Use small models. GPT 3.5, Claude Haiku, Llama 3.18b. These cost 10 to 50 times less than frontier models. Medium tasks, summarization, structured extraction, basic reasoning. Use mid-tier models. Claude Sonnet, GPT-4o-mini. Complex tasks, multi-step reasoning, coding, nuanced analysis. Only then do you reach for GPT-4 or Claude Opus. In interviews, the answer they want to hear is, I'd build a routing layer that classifies query complexity and dispatches to the appropriate model tier. Strategy 2. Caching, the most underrated cost lever. Think about it. In a customer support chatbot, 30 to 40% of queries are semantically similar. Why pay to answer the same question twice? There are two types of caching to know. Exact caching, store the response keyed by hash of the exact prompt. Trivial to implement. Massive wins for repeated, identical queries. Semantic caching. Use vector similarity to find cached responses for queries that mean the same thing. Store embeddings of past queries. Set a similarity threshold, like 0.92. Return cached response, if match found. Tools like GPT Cache, Redis with vector support, or even Pinecone work here. The interview follow-up question is always, what's the risk of semantic caching? Answer. Stale or incorrect responses if your threshold is too low, or if the underlying knowledge has changed. You need TTL, time to live, and cache invalidation strategies. Strategy 3. Prompt compression and context window management. Your biggest hidden cost is often unnecessary tokens in the prompt. Engineers add verbose system prompts, repeat instructions, include too much conversation history. Techniques to optimize. First, prune conversation history. Don't send the full chat history. Use a sliding window of the last 5 to 10 turns, or a summarized version of older context. Second, compress your system prompt. Use concise instructions. Test with shorter prompts and measure quality degradation. Often you can cut 30 to 40% of system prompt tokens with no quality loss. Third, use structured outputs. Instead of asking for verbose explanations, ask for JSON with specific fields. This reduces both input tokens from lengthy examples and output tokens from unnecessary prose. Fourth, implement token budgeting. Before each call, estimate token usage. If the conversation history is pushing limits, summarize it using a cheap small model first, then use that summary in the main call. Strategy 4. Batching and async processing. Not every AI call needs to be real-time. Identify which features are latency sensitive and which aren't. Real-time needs. User-facing chat, instant recommendations. Async is fine. Analytics, background summarization, document processing, report generation. For batch workloads, most providers offer batch APIs at 50% discount. OpenAI's batch API, Anthropic's message batches. These process within 24 hours at half price. For offline tasks, this is free money. Strategy 5. Fine-tuning for cost reduction. This is a longer-term play but important to understand. If you have a narrow, well-defined task, Fine-tuning a small model to match a large model's performance is often cost-effective. Example: instead of sending 2,000 token prompts with many examples to GPT-4, fine-tune GPT-3.5 or an open-source model on 1,000 examples. Post-fine-tuning, you can use a much smaller model with much shorter prompts. The break-even calculation interviewers love: fine-tuning costs X dollars upfront, but saves Y dollars per query. At what query volume does fine-tuning pay off? Know how to do this math. Strategy 6. Self-hosted open-source models. For high-volume workloads, deploying open-source models like Llama 3, Mistral, or Phi can dramatically cut costs. The trade-off: infrastructure overhead, maintenance, and potentially lower quality. When to recommend self-hosting in an interview. High-volume, predictable workloads. Data privacy requirements. Can't send data to OpenAI. Specific domain where fine-tuned open-source beats general frontier models. Budget constraints that make per-token pricing unsustainable. Tools like vLLM, TGI, text generation inference, and Llama make self-hosting much more accessible now. Let's talk about the monitoring piece, because cost optimization without measurement is guesswork. You need per-feature cost tracking. Know exactly how much each feature costs per user interaction. Use this to prioritize optimizations. Fix the expensive features first. Set cost alerts. If your daily LLM spend exceeds a threshold, you get paged. This prevents bill shock. Track cost per outcome metric, not just cost per query, but cost per successful task completion or conversion. A more expensive model that doubles conversion rate might be worth it. The interview framework answer 4. How would you reduce LLM costs? Step 1. Profile your current usage. Where are the most tokens being spent? What's the cost breakdown by feature? Step 2. Quick wins. Implement caching, prune prompts, switch simple tasks to cheaper models. Step 3. Architectural improvements. Add a model routing layer. Implement semantic caching. Move batch workloads to batch APIs. Step 4. Long-term. Evaluate fine-tuning for high-volume tasks.